All right, let's go ahead and get started. Welcome, everybody. My name is Andy Dessler. I am one of the hosts of our ECS and Cloud Feedback Virtual Symposium. Christy reminded me this is pretty close to our 3rd anniversary event. So it's been going on for 3 years. But thanks for everyone for attending. So let me just go over some of the details of the event. So we're going to have 2 AGU style talks, questions after each, and a general Q&A after the last talk. If you have questions or comments, you can type them into the chat at any time. So we have really good chat discussions in the chats, and those will all be archived. So feel free to type in your questions or your comments. If you want to ask a question live, just raise your hand and we will, I don't think we actually have to unmute you. I think people can unmute themselves, but everyone should be muted, by the way. But you can unmute yourself and ask the question. And just to let you know, our executive committee is Nick Lutzko, Sheila Lee, myself, Christy Prosescu, and Jonah Bloch-Johnson. If you want to give a talk or you have any suggestions, feel free to email us. We're always looking for volunteers to give talks. So definitely email one of us or all of us. We also have a website where we have the archives of all the previous talks, and a recording of this will be put up online after it's done. And lastly, just to let y'all know, we're going to be switching our emailing infrastructure from MailChimps to Google Groups. I think people on this group may have actually accidentally gotten a few emails from me last week. I didn't realize those were going out to the whole group. We're testing out the Google Groups infrastructure, and we're going to be switching over to that. So look for emails from the ECS Virtual Symposium Google Group, and that's how we're going to be communicating with everybody in the future. Hopefully, this will go painlessly, but there's a chance it won't. But certainly email us if you have any questions, like you're not getting emails or there's some other problem. And with that, I will turn it over to Sheila Lee, who's going to do the introduction of the speakers.
All right, I think I'm going to do the introductions.
Oh,
yeah.
Okay. Is going to handle Q&A.
All right.
Welcome, everybody. We have 2 speakers today. One from the National Center for Atmospheric Science in the UK, one from the National Center for Atmospheric Research in the US. So we're going to start with Jonah Bloch-Johnson, who is a postdoc at the University of Reading and the National Center for Atmospheric Sciences, and who has a PhD from University of Chicago, and is going to talk to us today about a simple model for nonlinear feedbacks. Take it away, Jonah.
Thank you so much, Christy. Can everyone hear me all right?
Good.
Yeah.
Okay, great. So yes, I'll be talking about a simple model of nonlinear radiative feedbacks. So, here we go. So suppose we define the global mean radiative feedback to be the dependence of the global mean net top of atmosphere radiative flux on the global mean surface temperature. By now, everyone at this symposium is familiar with the idea of the pattern effect, which is just that this number can change with time because feedbacks vary spatially, so that as the spatial pattern of temperature evolves in time, it sets off different feedbacks. Now, this is usually formulated mathematically as follows. So usually you can construct a vector of spatial feedbacks in which each element is the dependence of the global mean n on the surface temperature in each grid cell of a discretization of the surface of the Earth. And so if one wants to find the response to a given pattern of warming, you can just take the dot product of these spatial feedbacks with the surface temperature pattern. You can get the resulting change in global mean n. So this is a linear spatial model, and it allows us to produce a pattern effect. And the nice thing about a linear spatial model is that it also allows us to take a Green's function approach. So we can overlay the surface of the Earth with a bunch of patches. And for each patch, we can run an atmosphere-only model simulation where we perturb that patch's temperature, and we can find the resulting change in global mean N, divide by the change in the surface temperature, and get an estimate of the feedback associated with that patch, interpolate between them to get a whole map of spatial feedbacks. A number of people have performed this method, and this is a figure from a protocol paper for a MIP that we're actually now doing on Green's functions. You can find this paper online. It's a preprint is now available. So stay tuned for more GFMIP news and such things. But you can see that these different models all have somewhat similar spatial feedbacks, strong negative feedbacks in regions of tropical convection, especially the Western Pacific. We can test how well this Green's function method works by taking a atmosphere-only model and running it with, say, the time series of surface temperature from the historical period, while holding the forcing and sea ice constant, and then convolving or multiplying that same surface temperature time series by the Green's function estimated spatial feedbacks. So here I've done this for HAT AM3, and you can see that the Green's function estimates of the change in global mean N are pretty similar to the simulated values of the change in global mean N in HAT AM3. So in this case, the Green's function seems to be doing pretty well. However, if we instead use the temperature pattern from an abrupt 4-time simulation, say HAT CM3's abrupt 4-time simulation, then the Green's function estimate is too negative. It overestimates the magnitude of the response of global mean N to this temperature pattern. And HAT AM3 is not alone in this. This is a similar issue came up with CAM4 with the untuned version of the Green's functions from GFDL AM4, and in case studies over the tropical Pacific with CAN ESM5 and ICON. There are some models where it works better, such as Chenja's recent paper shows that with CAM5 it works a little bit better, but at least for these models, there seems to be something amiss, too strong of a response. And I think by now we have a pretty clear sense of why this is happening, which is that patch perturbations have pretty strong nonlinearity associated with their responses. Andrew Williams gave a really nice talk at the last symposium about how the responses are asymmetric to warming versus cooling. I'm going to talk about a different nonlinearity, which is that the smaller your patches are, the stronger the feedbacks associated with them. So here we have a case study over the tropical Pacific, where you have, this is with HAT AM3, where I have a range of patch setups all the way from a uniform perturbation over the entire domain to a bunch of quite small patches over the domain. Here is an estimate of the feedback associated with uniform perturbation for a warming of 2 degrees. And here is the map of spatial feedbacks for this small patch setup. You can see that obviously you're going to have more spatial variation when you have many different patches as opposed to uniform perturbation, but you can also see the feedbacks are much more negative when they're negative at all. So specifically, if we take the average over these 2 domains, the the domain mean average for the small patch setup is much more negative than for the uniform setup. If we fill in all the cases in between, it changes pretty smoothly from one to the other. I think that Andrew Williams's circus tent hypothesis from last time is a good potential explanation for why this occurs. So this hypothesis says that deep convection occurs when surface moist static energy exceeds the saturated moist static energy aloft. So that if we were to warm one of these deep convecting regions, it would increase the surface moist static energy and give a new source of higher surface moist static energy, saturated moist static energy aloft. That would increase the broad lower tropospheric stability, therefore increase low cloudiness, and thus increase reflected radiation. And that's the negative feedback associated with regions of deep convection. Suppose that we have 2 regions that are close to each other, and we want to know what it's would be like if we warmed both of these regions at the same time. And we know what it's like if we warm them in isolation of each other. If things were linear, we could simply look at the change in the atmosphere in response to the warming in the first region and the change from warming the second region, and then add them together. And we would probably get something like a response of the cloudiness and the radiation that was twice as strong as warming in either of the regions on their own. However, in simulations, we actually get less than that. And I think this is because there's some sort of negative cross term. So the increased moist static energy lost from the deep convection from one of the regions tends to suppress the deep convection of the other and vice versa, so that you don't get as strong as a result as you would get if they were both, if you just added together their individual responses. A similar result holds for cooling, but I don't have time to go into that right now. Suffice it to say that I think there's something that I've given the somewhat silly name of the patchiness effect. The patchiness effect is this idea that perturbing a region's surface temperature more than its surroundings produces a stronger response than if the surroundings were also perturbed. And this is a bit of an issue for using things like these patch Green's functions to understand the response to relatively smooth or uniformish patterns like you sometimes get with abrupt 4-time simulations. One potential way around this, or a way of addressing this, is to use fewer and larger patches. So here I'm going to try to use just 2 patches. So here's our map of spatial feedbacks. I mentioned that you get quite negative feedbacks in regions of tropical ascent. So this is vertical velocity for the HAD-CM3 PI control climatology. And I'm going to just draw my 2 regions to be regions where you have tropical ascent and everywhere else. So we can use these regions as basis for patches, which we can use to estimate spatial feedbacks. And then just as we can try to estimate the change in global mean n using the full Green's functions, we can do so with the 2-region model. It doesn't do as well as the full Green's functions, but it still does pretty well. It does better than assuming a single uniform feedback. However, when it comes to the response to the abrupt 4-times pattern, it does much better than the full Green's functions, and it still does better than assuming a single uniform feedback. Now, so far we've just been considering the response, feedbacks in response to warming of up to say 4 degrees or so. Once you go beyond this, as I did in these simulations with HAD-CM3 here, you can start to get big changes in your feedbacks and the physics behind them, such as changes in the water vapor feedback or just changes in circulation and cloudiness, so that you can get really nonlinear behavior like this sort of runaway warming we see under 3 doublings of HAD-CM3. The 2-region model actually can help us to capture this effect as well. So I'm going to show some figures here that are a little, might look a little bit unusual at first, but I'm going to explain them. So in each of these panels, I've run atmosphere-only simulations where CO2 is set to 2 times, 4 times, and 8 times the pre-industrial level. And for each of these squares, I've perturbed the temperature in these 2 regions. And then found the resulting change in global mean n. And if I interpolate between them, I get these surfaces that look pretty wild. But if I plot the time series of warming in these 2 regions and use that to estimate the change in global mean n, I get these black dots, which do a pretty good job of matching the actual simulated values, which is to say that this nonlinear 2-region model seems to capture both the pattern effect and the feedback temperature dependence of this coupled model. Now, I said that this looks pretty wild, and it does, but it's actually makes a little bit more sense than it might seem to at first. So if we consider we look at the lines that are close to the abrupt 2 times simulations, you can see that a lot of them are kind of parallel to each other. So it suggests that, at least for the values around the abrupt 2-time simulation, this is still pretty linear. So we can take the simulations specifically from these regions, and we can fit them with a linear model, a spatial linear model like before. And this model does a good job of capturing the behavior of the abrupt 2-time simulation and the beginning of the abrupt 4 times and abrupt 8 times. If we subtract this from the full pattern, we get these residuals that actually look much more coherent. And there's really just two things going on here. If we increase the, if we move along a uniform warming line, then we get this sort of parabola-like shape. And so there's some sort of second order term associated with uniform warming. If we move along a line of constant global mean warming, but a change in the difference in warming between the two regions, we get this sort of cubic. And so it suggests that we could construct a polynomial model with 5 terms. That's a polynomial version of this 2-region model. And so the top is the actual full simulations, and this is the polynomial model. And it does a pretty good job of capturing the broad behavior of all these simulations. It's and a pretty good job of getting the actual simulated values of the full GCM. Now, this model provides us with a way of understanding what's going on in these plots. The first two feedback terms represent the linear pattern effect. So these are sort of like the spatial linearity, like we began the talk with. The third term is the uniform feedback temperature dependence term, which just tells you the change from nonlinearity from being in a warmer world. And finally, these last two terms represent the patchiness effect, the nonlinearity you get from perturbing one region more than another. You might notice that the simulations never go into the regions where you would see a significant patchiness effect. So you might be inclined to say that maybe it's not actually an important effect for realistic temperature patterns. And in fact, if we remove those terms and just focus on the simulations that are close to the more realistic abrupt patterns, we can fit them with just these 3 terms and we get even a slightly better fit. However, the patchiness effect is much stronger when you are looking at warming that's more concentrated. Again, as I was talking about before, the smaller your patches are, the stronger this effect. And so this 2-region model by construction does not have very concentrated warming. So I have results I could talk about around, in which I demonstrate this for specific patches, but I'm just going to show one example here where we have our reconstruction of the responsive global mean n to the historical pattern, the temperature pattern. And I'm going to zero in on one year, which is 1998. This is one of the years where the 2-region model does really poorly. And the temperature pattern for this year is an El Nino like pattern in some ways. It's quite concentrated in the East Pacific. This is the black dot is the simulated value for HAT AM3, and the green dot is the 2-region model estimate of what you get. I can make another pattern that has the same average warming in the 2 different regions of the 2-region model, is over here. And so this black dot is now the simulated value for this pattern, which is very close to the 2-region model. And then I can linearly interpolate between the two. And what you can see is that the Green's function reconstruction, the full Green's function reconstruction, is actually pretty close to the 2-region model. It doesn't change that much, which I think means that what's happening here, the reason that we're getting this big increase in the magnitude of the change in global mean n, isn't that there's a linear pattern effect. It's that there's a patchiness effect. It's that the temperature is getting change is getting concentrated in certain regions. So All this is to say, I think we need to account for this if we want to understand the behavior of particularly anomalous years. So to conclude, a linear two-region model can roughly capture the pattern effect in HAD-CM3 for historical and abrupt 4x patterns, at least when the warming is less than, say, 5K. For additional warming, uniform feedback temperature dependence term captures further changes in the feedback. If we want to get better accuracy, especially for anomalous years, we need more regions and to account for the patchiness effect. I think GFMIP will really help with this, especially for understanding the patchiness effect, which right now we're still in the early phases of. So anyway, thank you for listening, and I'm happy to take any questions or comments.
Thanks, Jonah. That's a great talk. So any questions for Jonah? I haven't seen any in the chat. So again, you can, oh, we got one. Yeah, Andrews, please go ahead.
Hello, thanks for the nice talk. Just a quick question about the runaway feedback for 8 times CO2. Do you know if is that water vapor feedback or cloud feedback? Do you know what it's causing? What's causing it?
It's cloud feedback on top of the, so it seems like most models have a positive water vapor feedback temperature dependence, but it's usually not enough to cause something like that on its own. So I think it seems like with HAD-CM3, it's also that there's a temperature dependent cloud feedback. Specifically, there's just a complete reorganization of the circulation in the tropics that tends to get rid of a lot of low clouds. So I think it's also that.
Okay, thanks.
No problem.
Any other questions? Okay. We have one in the chat from Jiang Zhu. Yeah. Hi, Jonah. Thanks for the great talk. Do you expect the polynomial fate has large model dependence? Can we use that from hardly CM to predict CESM results?
Thanks, John. That's a good question. I do expect that there's probably very large model dependence. It's possible that this type of simple model doesn't even work very well for other models. I know that I think in that same paper from that Zhou et al. Paper that recently came out, there was some attempt to use a sort of quadratic term to capture a uniform feedback temperature dependence, and it turns out that for some models it just wasn't as good as something like something that had more like a threshold beyond which the cloud feedback changed or something like this. But I'd be curious. I mean, I can try to apply this model to other GCMs, but I'm also curious, you know, for people to run these types of experiments, because the nice thing about this is you don't need to know the shape of your Green's functions, although it's good to run the Green's functions, but you just need to know where your ascent is. And that tells you where to draw your boundaries for your two-region model. But anyway, thank you.
Okay, there are two more questions in the chat. One is from Bo Song. Regarding the uniform feedback, any explanation why it appears as a second order term?
So I should say that, thank you both for that question. I should say that there still is a first order term that associated with the uniform. You can kind of think of it as if you have first order terms for the individual regions, it's like that will contain the first order term for a uniform response, and then the second order term is just you're trying to go one step beyond. There could be higher order terms too, especially for other models. So I hope that answers that question.
Yeah, one more from Kyle Amor. Thanks, Jonah. Have you looked at your framework of polynomial fit in the context of individual feedbacks? That is, does this work equally well for clouds, water vapor, and so on? Or does it work better for some feedbacks and worse for others?
Thanks, Kyle. That's a very logical next step for this, but it's not a step I've taken yet. But I'm very curious to answer that question. So I'll keep you. I'll let you know. I find.
Yeah, he said thanks. All right, if you have more questions for Jonah, you can save it for the general Q&A in the end.
Thanks, everyone.
Okay, thank you, Jonah. Our next speaker is Clara Desser. I don't really think she needs an introduction, but I will give her a short one anyways. She is a senior scientist at NCAR, and she is head of the climate analysis section in the Climate and Global Dynamics Laboratory. She's a fellow of the National Academies, AIGU, AMS, and I really look forward to her talk. Clara, take it away.
Thank you very much. Can you hear me?
Yes.
Okay, very good. Hi, everyone. This is my first time to join this wonderful virtual symposium. I look forward to your suggestions and comments on this work. I'm going to talk about Southern Ocean SST impacts on the tropics in two versions of the Community Earth System model, version 1 and 2. And this work is done with lots of people, Sarah Kang, UAU, Sally Zhang, and also Paolo Ceppi has joined recently. Oops. Sorry. Okay, so the question we're investigating is, what is the influence of observed Southern Ocean cooling in recent decades on the tropical Pacific? And we're going to try to address this question using coupled ocean atmosphere, global coupled ocean atmosphere simulations. So the map that you're seeing here are the observed SST trends from 1979 to 2013. I think they would look largely similar if they were updated to the present. And very notable, of course, is the cooling that has been observed in the Southern Ocean. And the question is, to what extent does that affect climate in remote regions? So I'd like to point out that there is some observational uncertainty about the magnitude of this cooling. This lower map is an earlier version of the NOAA ERSST data set, so-called V3B. And it also shows cooling in the Southern Ocean, but the magnitude is somewhat weaker. So there is this observational uncertainty. I will say that the newer version, the top map, version 5, has much more data in the Southern Ocean compared to the earlier version. So perhaps it is more trustworthy, but we still have to be aware of this observational uncertainty. So what I want to do here today is to summarize a comparison between experiments with, as I said, the two versions of CESM. And the experiments that we're conducting are the so-called pacemaker protocol. So you have a global coupled model. And in the region of the Southern Ocean, which we are defining as south of 40 South, we nudge the model's SST anomalies. That means deviations from the model's climatology. So the model's biased climatology is kept intact. And we're just nudging the model's SST anomalies in the Southern Ocean to follow the observed evolution of SST anomalies. From 1970 to 2014, I'm hoping we can update these runs in our next phase of research. So what we've conducted these experiments, as I said, with both CESM1 and CESM2. And the two sets of runs differ in their observational data set, which is why I showed them to you. And that's just because when we did the runs led by Sally Zhang, that was when we had the V3B data were the latest available. And then with CESM2 in the last year, we've been able to make use of the RSST V5. So they do have different SST data sets. So for each of these experiments, we run a 20-member ensemble with slight perturbations to the atmospheric initial conditions at the first time step in 1970. And all ensemble members also have historical radiative forcings applied throughout the simulation. So to account for, to take into account this difference in the magnitude of Southern Ocean cooling, especially in the Pacific sector, that is apparent between these two different observational data sets. We've actually multiplied the CSM1, the SST anomalies in the Southern Ocean in the SST V3b, the anomalies, by this factor 1.22, and that comes from this region in the box, in the blue box, the Pacific region of the Southern Ocean, which you can see by eye. It's about 20% stronger in the V5 version of the data compared to the V3b. So we're just taking that into account in our simulations. Okay, so then we take the ensemble average, that's denoted by the brackets here, and the acronym is SO-PACE, meaning Southern Ocean Pacemaker. The 1 refers to that it's conducted with CSM1, and the 2 refers to the experiments with CESM2. So this ensemble mean, with assuming 20 members is a reasonable number, will show the forced response to the influence from the observed Southern Ocean SST trend plus the response to the radiative forcing. So that's what you get with this ensemble mean. So here are the results. This is the global SST trend map for that same time period from the SO-PACE 1 and on the top and SO-PACE 2 on the bottom. That blue line demarcates 40 south. So south of that is the observed Southern Ocean SST trends, and you can see that slight difference in their pattern because of the different data sets used. The magnitudes are made to be about the same for that Pacific sector, as I just mentioned. So this is what it looks like, and you can see already by eye that the response to observed Southern Ocean cooling and radiative forcing is somewhat is a stronger and more significant cooling response in this region of the Southeast tropical Pacific. So now we want to understand where that comes from, and we have to take it apart into its radiatively forced component and the influence from the Southern Ocean. So here on the left, I'm showing you what the equivalent for each model. We have a large ensemble of just freely running historical simulations. So on the top left, that's the 40-member large ensemble with CSM1. And on the bottom left, that's the 100-member CSM2 large ensemble. So we take the ensemble mean, denoted by the square bracket, and this is the model's response to radiative forcing. Note that for CSM1, CMIP5 radiative forcing is used, and CMIP6 for CSM2, and I'll get back to that in a moment. So that's what that looks like. And then we assess the role of observed Southern Ocean cooling by taking the difference. So sorry, I swapped it. It should be SO-PACE minus historical. And that's what then shows what is driven by the observed Southern Ocean cooling. So I have the columns reversed, but I think you can follow what we've done here. So SO driven means what is driven by the observed SST trends in the Southern Ocean in these two ensembles with CSM1 and 2. So immediately evident is that if for CSM2 there is a stronger and more significant tropical SST, Southeast tropical Pacific SST response in CSM2 than CSM1. So that's sort of the leading conclusion here, and we'll continue to I'll show you why that occurs. And then the second interesting point is that there are opposite signed responses in the North Pacific, and these are significant. And I think it's very interesting to understand those. We haven't done too much to understand them, but we have some hypotheses about that. So two notable differences: the enhanced cooling in the Southeast Tropical Pacific was CSM2, and the opposite side response in the North Pacific. Okay, so now we do a mixed layer heat budget analysis to just try to understand the leading mechanisms for the cooling in this box in the Southeast subtropical Pacific. And I'll show you that next. So here we're following the methodology that Sally used in her paper in 2021, where you look at the heat budget for the trends and assume that the tendency, the time tendency of these long-term trends is zero, which we've shown in that paper is a good assumption. So then you sort of have a balance between terms, which you can write as a diagnostic for the trend in mixed layer temperature, which is shown in that bottom equation. I don't have time to go through all the terms, but it's obviously the trends in the short wave, the long wave, the latent heat flux divided into non-Newtonian terms, that's called others, and then the sensible heat flux, and then trends in ocean heat transport, and then divided by the Newtonian component of the latent heat flux trend. Okay, so here are the results. So this is for that region in the Southeast Pacific. These are the terms that for the mixed layer heat budget in degrees Kelvin per decade. So first, I'll point out what these two terms are. So on the left are the actual trends in SST in this region. For the Southern Ocean driven component, the red is from CSM1 and the blue is from CSM2. So you can see that sort of doubling of the cooling that was evident from the maps for CSM2. Then the next term, delta T sum, that is just the summation of all the terms, and it provides a nice check that we're actually, the heat budget is actually in balance, and that we are recovering roughly the same magnitude as the actual trend itself. So that's just a sanity check. Okay, so now we move on to the terms in the heat budget, and it's clear that the shortwave trends in the shortwave fluxes are the dominant cooling term for this region. And then the next leading term for cooling in this region is the non-Newtonian component of the latent heat flux, so primarily via wind changes and also air-sea humidity differences. And then to balance those cooling terms in steady state, this is largely accomplished by changes in the ocean heat transport and changes in the long wave flux. So the reason why the shortwave flux is greater in CSM2 than 1 is a larger low cloud SST feedback. And Paolo Ceppi has just provided, actually just in the last few weeks here, a beautiful calculation using the cloud controlling factor analysis method, I believe following Myers et al. In 2021, and also Paolo's much more recent work with Peter Novak. So here for this region of the Southeast Pacific, we take AMIP runs forced by the observed historical SST evolution, and we look at this partial derivative of the shortwave cloud radiative effect from low clouds as a function or as partial derivative with SST for this region. And for observations, he's used the MODIS cloud radiative data and the ERA data for the other fields. And for this region, he estimates for the recent few decades, this partial derivative is 2.21 watts per meter squared per degree Kelvin. CSM2 agrees incredibly well with this observed estimate. So you can see that from the numbers there. So it's extremely realistic, whereas CSM1 really strongly underestimates this low cloud SST feedback. So that's really why the CSM2 has this stronger response than CSM1. Okay, so now I want to move on to a few points here. Okay, so now we come back to our maps, and now I've added this lower map in the middle. That is the observed ERSST V5 SST trend. The stippling is not significant, but it's still, interesting to see the pattern. So that's the global pattern. And the question is, how much of that pattern can be recovered from these Southern Ocean pacemaker ensemble means? And you can see that there's some similarity, maybe south of the equator with SOPACE2, and maybe a little bit less with SOPACE1. And then large differences are found north of the equator, especially in the North Pacific, where this PDO-like pattern is really not apparent in either of the pacemaker experiments. So on the face of it, Southern Ocean pacemakers, I would have never expected them to reproduce the observations, but certainly they are showing some evidence of cooling that penetrates into the Southeast tropical Pacific. So I just want to come back to this fact here that these historical experiments with CSM1 and 2, the radiative forcing is different. And you might think for the historical time period that hasn't changed, that the historical radiative forcing wouldn't be any different between CMIP5 and CMIP6. In fact, there are differences, and I think this is a very important area that needs to be investigated a lot more. So here at NCAR, Marika Holland and Jen Kay have led a really interesting experiment. So they took CSM2, and instead of forcing it with CMIP6 forcing, which was done for the large ensemble, they used CMIP5 forcing. They ran a 15-member ensemble, and here are the trend maps, or the trend map in the lower left. I call it HIST3. It's simply the CSM2 model forced with the CMIP5 historical radiative forcing. So you can see that compared to the same model with CMIP6 forcing, it gets a much more muted warming in the northern oceans, and it has sort of a PDO-like structure in the North Pacific, although it's offset by uniform warming in that region. And then you can compare that bottom HIST3 with HIST1. So those have the same radiative forcing, but different model versions. And again, that's how you can see that there are structural differences in climate sensitivity between the two models. So it's sort of a nuanced point that I think is really important to appreciate, that not only have the models that we're using changed, but also the historical forcing. So the last point here is that we have made up a synthetic Southern Ocean pacemaker run with this 15-member CSM2 historical runs with CMIP5 forcing. And the way that we did that was that we took this HIST3, so that's CSM2, CMIP5, and we took the Southern Ocean driven response in CSM2, and we added them together. So this is our poor man's synthetic Southern Ocean pacemaker with CSM2 with CMIP5 forcing. And to my eye anyway, and I'll quantify that in a moment with pattern correlations, I think you might agree that the south of the equator, actually, this synthetic Southern Ocean pacemaker has the strongest resemblance with the observations. And it even in the northern north of the equator, it even gets, I would argue, the patterns perhaps in the North Pacific better than the other two pacemaker runs. So I'm just putting that as food for thought, that we also have to consider what's changed in the historical radiative forcings. Okay, so now we'll go on to make more quantitative statements here. So we're going to do pattern correlations for the region between the equator and 40 south. So we're not including the region where we have nudged the model. Obviously, that would not be fair. And we're just looking at south of the equator where the SST response to the Southern Ocean is most significant. So I'll walk you through this diagram. These are pattern correlations for the SST trend maps that you just saw for the region between 40 south and the equator. And first, just pay attention to the triangles. That's simply the pattern correlation between the observed trend map and the ensemble mean of the different model experiments. So, i.e., their forced response and how much the observed trend map resembles the forced response in these different experiments. So if you move from, for each of these pairs of colors here, if you move from the historical experiments, the HIST, to the triangle for the SO PACE experiments, that shows you the influence of the observed Southern Ocean cooling on this pattern correlation. And for all three model configurations, the correlation with SO PACE is higher than the correlation with the historical experiments. So that does indicate that there has been, a realistic shift in the pattern due to imposing the observed Southern Ocean cooling. The pink here is this hybrid synthetic runs that I was calling HIST-3 in my previous slide, just to make that clear. And then we can look at the box and whisker plot, and that is showing the distribution of pattern correlations using each ensemble member correlated with the model's ensemble mean. So just like the observations can be thought of as one ensemble member, we've done that same calculation for each of the ensemble members. So you can see the spread. And the conclusion or takeaway here is that the triangles, so the correlation of the observations with the Southern Ocean pacemaker runs lies within the ensemble spread only for the two CESM, the blue and the pink, if you look at the right-hand bar and whisker plots for those. And CSM1, that triangle, lies just below the minimum correlation across the models. So there seems to be, that CSM2, with its stronger low cloud feedback, does seem to make it, give it more realism. And then the third takeaway is that although it's just marginally higher, the correlation is between the observations and the Southern SO PACE with CSM2 is slightly higher when you use CMIP5 forcing than CMIP6 forcing. So I think that just brings some attention to that we need to really scrutinize the forcings to understand that. Okay, and then in our paper submitted to PNAS, we're just completing the revisions, about to submit that. We have additional results for sea level pressure, precipitation, Hadley circulation, and Antarctic sea ice. I'm happy to show you those results as well. And thank you so much for your attention. Happy to answer any questions.
Well, thanks, Clara, for the nice talk. So today we only have 2 speakers, which leaves us about 10 minutes of our discussion. And there are already a bunch of questions for Clara, but just a reminder, if you have questions for Jonah, please put it in the chat as well. So first, we have Gavin Smith made a couple of comments and a question in the chat. Gavin, would you mind unmute yourself and asking a question yourself?
Sure. Thank you very much. Thank you very much, Clara. That was very interesting. How does the sea ice respond to the SO PACE temperatures? Is the sea ice like responding to the underlying real ocean temperatures, or is it connected to what you forced onto it?
Well, because we have strongly restored the coupled models SST, we really have, cut off the influence from the, the mixed layer and the ocean depth beneath it. So we really can't address how the SST cooling in the Southern Ocean originated. That's just not what these experiments are designed to address. So if I think maybe you're getting at but in regions of sea ice in these pacemaker experiments, the temperature in regions with sea ice is set to the freezing point, minus 1.8 degrees C. So we actually, in regions with sea ice cover, we actually hold that SST fixed at the freezing level. There are, I probably don't have time to describe this figure, but there are, and I have the PDF posted on my website if you're interested, the original version. But the CSM2, actually, the Southern Ocean pacemaker with CSM2 actually gets a bit more realistic Antarctic sea ice expansion compared to CSM1, but you can look at that in the paper. Thanks for your question.
Okay, we have another question from Chris Holloway. It is interesting that SO Pace 1 has much stronger cooling in the Labrador Sea region. Does that link to the AMOC?
Yeah, that's an excellent observation. It is linked to AMOC, and I have to say, of course, we noticed that, but I hadn't quite noticed that it is stronger. I guess it's maybe not stronger it's stronger in an absolute sense, but perhaps not in a relative sense. Because if you look at SOPACE 2, that middle map, the cooling, although it's muted, is surrounded by much more warming. So maybe in a relative sense, AMOC, has a similar response. But to be honest, we haven't looked at AMOC and this comparison, I think, between AMOC and these two SOPACE experiments. So I appreciate your question, and we will do that, and I'd be happy to get back to you.
Great. The next question is from Chris Burston. Are the imposed Southern Ocean SST anomalies larger than the internal variability of the CASM1 and 2 ensembles? How far out of energy balance is the Southern Ocean itself in these simulations?
Yeah, really great questions, Chris. Let's see, I don't have it in my presentation, but we have a figure in the supplemental materials to show the spread of, the Southern Ocean SST trends produced by the coupled model and the comparison with the observations. I have to say, I just don't remember the result right now, so I will follow up with you on that. Excellent questions, appreciate it.
Next question is from Dave Bona. Have you performed the pacemaker experiments with smaller Southern Ocean domains? Yue Dong has a nice paper showing the impact of Southern Ocean cooling on global SST trends. It's sensitive to the longitudinal location of forcing in the Southern Ocean.
Great question. We have not done that.
Okay. The next question is from Ian Eastman. Do you want to unmute yourself and ask your question, Ian?
Sure, because it's a little bit long. So Clara, thanks for a great talk. I'm just reading what I wrote here, but thinking about your results with Jonah's talk in mind and also Dave Bonan's comment in mind, would you expect pacemaker simulations like this to linearly add up, meaning to linearly add up in the sense that Jonah's patches added up? So more specifically, if you took the global surface area outside of the tropics and separated it into a set of regions and then did pacemaker simulations with each region where you nudged one by one the SST in each region to match observations. And then you looked at the anomalous tropical SST associated with each simulation, would you expect these to linearly add up to match the observed SST?
Yeah, great question. Oh, sorry, go ahead.
Well, I was just going to say, if you wouldn't,
yeah,
in what sense does that imply that a given region here, the Southern Ocean, would be driving the tropical SST?
Yeah, great questions. And I also wanted to just tell Jonah, I appreciated very much the points that you were making. I think it's makes a lot of sense to me that things don't add up, that, you know, one region's influence on another can be counteracted by, you know, another area. So I fully, you know, buy into that. And yes, I agree that the same thing could be happening with the Southern Ocean. Maybe one thing in favor in what the results I've showed, as you can see from the maps, is that the cooling in the Pacific sector of the Southern Ocean is certainly a lot stronger than the cooling in the other sectors. But one cannot rule out, you know, that the Atlantic part of the Southern Ocean could impact the tropical, southeast tropical Atlantic, which could then have some tropical teleconnection to the tropical Pacific. So yeah, I wouldn't be surprised that those interactions are going on. And I think that's great food for, you know, thought for follow-up experiments. And then the other point I want to make is that I don't think we should interpret the Southern Ocean, especially the Pacific sector, as being independent of the tropics. I think it's very much chicken and egg. Some of that cooling in the Southern Ocean, Pacific sector is probably driven by the cooling in the tropical Pacific. And I think Yue Dong's work has shown that very nicely. So we're just looking at that feedback then to the tropical Pacific, but it is very much sort of mutual influence.
Okay, I think we have time for a couple more questions. The next one is from Karsten. He asks, any guess what's causing the larger SST local feedback in CSM2? Does the SO pace 2 for that matter, or the changes in cloud microphysics?
Yeah, I know that a lot, you know, had been done in terms of changes in cloud microphysics for CESM2. And I'm sorry that I can't speak to the details. There are, I think, Andrew Gettleman and Brian Medeiros. I think that they're the ones who have led a paper on that detail changes in the microphysics. I'm not sure that this particular region was called out in their paper. So I can't speak to it, and it's a great question, and I'll try to educate myself more thoroughly on that so I can respond, get back to you as a follow-up. Thanks.
And the next question is from Isaac Held. Is there a significant change in ENSO statistics in either model?
That's a nice question. Haven't looked at that. I think we may have looked at it a little bit early on with the SO PACE 1, and we just didn't have a strong enough response, you know, to see anything that was significant. But it would be intriguing to look at SO PACE 2. Thanks for the question, Isaac.
Okay, it's up to 1 hour, but we do have another discussion about biomass in the model. So if people have any other schedule, feel free to leave. But we're gonna, if Clara, if we have time, we can move on. Yeah, for the next question, and it's from Kyle Amargan. So it's related to what Gavin Schmidt asked before. So Kyle Amar, will you be able to ask the question yourself?
Sure, I can ask. My question was really just what is the difference in the two forcing data sets here? Gavin mentioned biomass burning as kind of a problem in the original CSM2 data set, but I was curious if you thought about, or if people have looked at what has changed in the forcings between the two data sets and what has led to these big differences in pattern in CSM2 when you run with these two different data sets.
Yeah, and sorry, I must have missed that Gavin had mentioned biomass burning. I think I focused on the ocean at depth part of his question. So yes, biomass burning is definitely a big difference. And in the large ensemble version 2, which I helped to design, and John Fasulo really discovered that there was a big issue with the discontinuity in not the mean biomass burning, but the variability in biomass burning before the satellite era of observations relative to before. And that discontinuity led to a rectified effect in the climate system. And I think some of that is showing up as in terms of this larger warming in the North Pacific in the HIS2 experiments. But then we ran 50 ensemble members with that discontinuity in biomass burning that nobody was aware of, and the impact of that. And then I decided to change course halfway through and then devote the second 50 members to having the same, just a smooth biomass burning. So we removed that component. So I have to say I'm a little foggy right now this morning on how much this trend map for HIS2 differs between the first and second 50 members, which would help us answer that question about the role of biomass burning. So I will follow up with you and Gavin. I'd be happy to do that once I figure that out.
Okay, I think that's almost everything for the discussion today. And once again, thanks our speaker, Clara and Jonah. And do you have any final comments, Christy, before we wrap it up?
No, just
Okay.
thanks the speakers.
Yeah, okay. I think if nothing else, we will see you in our next event. So see you in May. And bye, everyone. Take care.
Bye-bye. Thank you.
Bye-bye.